So welcome everybody to the webinar of today. The speaker of today is Ariane Gayout, and she will talk about fluid structure interactions on multistable pendular systems. As usual, I introduce the speaker and then I leave her the stage. Freshly graduated, Ariane Gayout has always been interested in flight and aerodynamics. After a scientific preparatory class, she joined the ENS de Lyon in 2015, which she is now living after 4 years as a undergraduate student and 3 years of doctorate in the physics laboratory. During these years, she specialized in fluid mechanics and more particularly in aerodynamics until completing her thesis on the study of a multistable pendulum in a wind tunnel. During her thesis, she set up a junior laboratory followed by a CNES-funded project on the flight of butterflies in weightlessness, the Phoebus project. For her work, she received in 2021 the Amelia Earhart Scholarship for doctoral students in aerospace and astronomy. In November, she will join the University of Groningen in a postdoc on the flight of falcons with Professor David Lenting. So it's a great pleasure to have introduced Ariane Gayout for the webinar of today. So Ariane, I stop sharing my screen and you can start sharing yours.
Thank you, Francesco, for the introductions. So yeah, it's are you all looking at my? Are you all seeing it?
Yeah, we see your screen in full screen mode, so that's perfect.
Okay, thank you. So thank you for inviting me today to present my PhD work. So as introduced, I will be talking about fluid structure interactions on multistable pendular systems, which I conducted at the Laboratoire de Physique of the ENS de Lyon with Nicolas Pion and Michael Bourgon, my PhD advisors. So the title seems a bit confusing at least. And there is three main topics in the subject, so pendulum, fluid, and multistability. So when we first think of a multistable pendulum, we would usually think about this kind of pendulum as it answers any of your questions you ask it. It tests your stability in health, in money, in love, and everything. And according to Yves Rocard, it's also sensitive to water sources. However, the multistable pendulum we are going to use is definitely not this one. We leave this to esotericism. So our pendulum, which we're going to place in a wind tunnel, looks like this. So we're going to have this rod, which is a saw blade sanded of 30 centimeter length, which on which we append a disc of about 4 centimeters. We can also vary the size, but for the following, we'll stay with a 4 centimeter disc. And we place it in a wind tunnel. So the two main quantities that are going to interest us is the wind speed velocity, U, which we record using hot wire and pyramid tube measurements. And we will record the angle of the pendulum as well using a potentiometer and frictionless encoder in order to remove as much noise as possible and as much damping as possible. So our wind tunnel is about 51 centimeter wide and of a square section, and we place ourselves at about 1.5 meters. So we have something of not so low turbulence, but not so bad either. So just a small review of what's going on in our pendulum. So when we are at equilibrium, the force in play are first the weight, which is applied about here because the aluminum disc is really thin and really light, while the saw blade is iron, so kind of heavy. And when we add the flow, then suddenly, as everybody does our fluid dynamics here, you know that it's going to induce drag and lift at the same time. So these are the three main forces we have here. There is, of course, the resistance of the blade, but we don't consider it here. So why are we talking about a multistable pendulum? So this is because when we place our pendulum in a flow, and so we place it with the disc facing the flow. So as we blow on it, we are displacing the equilibrium position with the curve here. And as you see, first it goes almost linearly up to a certain point for which a slight increment in velocity induces a huge displacement in angle. If we now lower the flow velocity, then we get access to angles which we didn't have access to before. And again, we arrive to another position here for which a slight decrease in flow velocity induces a huge decrease in angle. For this whole range of flow velocity, we have two equilibrium positions. So that's why we're talking about multistable, bistable pendulum. So we can understand the bistability really easily first. So first, we need to look into, we know that from a pendulum, when it's only the weight, we have no bistability. So it necessarily comes from the aerodynamic forces. If we take the drag force, then we can use dimensional analysis to get the Reynolds number and the drag coefficient CD. Which we are dimensionalized by the pressure, dynamic pressure, and the surface of the object. So for a sphere, we get this beautiful curve from Herner in 1965. And if we place ourselves in between Reynolds equal to 10.3 to 10.4, we're almost content. So we are able to remove completely the dependence in Reynolds. If the object is no longer a sphere, but a disk for us, then we get, and we no longer have the rotational invariance. So now we have a dependence in the angle of attack. And what we know from Flagstaff in 1932 is that when we place a disk and we look at its drag coefficient as a function of the angle, so 90 is the horizontal and 0 is the vertical, then we get this strange angular dependence with a sharp discontinuity corresponding to stall. We can do the same analysis for the lift, and we get this also the lift coefficient here, which also presents this discontinuity around 50 degrees. And so, as you may conjecture from now, this is going to be the origin of our bistability. So instead of looking at forces, since we have something that turns, then it's normal to look at the torques. And so our torque balance is between the weight and the aerodynamic. And in particular, the aerodynamical torques have two additional angular dependency with a cosine theta and a sine theta. And so we can look at the whole aerodynamic torque as only one of them through the normal. So we project both the lift and the drag onto the normal of the system. And the normal aerodynamic coefficient has this beautiful shape of being almost constant up to 50 degrees and almost linear to 0 with a discontinuity at 50 degrees. So these are data from 1932. And this will, and if we compare to the weight torque, then the dependence in theta is only a sine. So it's going to be really easy to see how it's going. So now if we put it together and look at the fluctuation with the flow velocity u, we see that only the aerodynamic torque is depending on the flow velocity, which is almost normal, I guess. And so if we are at low flow velocity, then we are like here, the equilibrium position is going to be the intersection point of these two curves. And here at low velocity, for instance, 4.5 meters per second for our pendulum, we are at about 25 degrees. If we increase a lot the flow velocity, we get this curve for which the equilibrium position is now at 65 degrees. And as we are moving the flow velocity continuously, then in between, we get 3 positions of equilibrium, 2 stable and 1 unstable. And this is so with only this small torque balance at equilibrium, we can understand the bistability. So why did I spend 3 years of my life studying this kind of pendulum? It's because if we add to it some dynamics and we place ourselves close to the edge of the bistable zone, then we get this kind of strange system where we have something that oscillates around its first equilibrium position and suddenly goes onto its other equilibrium position, spontaneously without any help. So today I will present a part of my PhD work by first studying this system as just a generic multistable system. Then I will focus on the static wave structure because first I will completely remove any fluid mechanics we might think of. Then I will put it back together, but removing any kind of dynamics, while bringing the two of them together by looking at the wave during the transition. And then I will just conclude of other aspects beyond the disk pendulum. For instance, changing the shape, changing the system overall and everything. So first, I will focus on the generic multistable system by looking at how we can characterize experimentally the spontaneous transition. And also, I will present a bit of an analogy with the transition to turbulence and a model based on this analogy. So, as I showed before, so here you stay at the constant flow velocity and you're placed here, and suddenly you just observe a jump. So you're happy, you have a spontaneous transition. But now that you have one, you want multiple of them. So you're gonna bring together an experimental protocol to pursue them and get statistics on them. So you're gonna cycle through the hysteretic cycle induced by the bistability. And first, you're going to stay for a few minutes at the U-trans, so a transient flow velocity. Then you will bring the flow velocity to its test value, you will wait for a given time, like it can last a few hundred seconds, even a few hours, in fact. And here it's like 20 seconds. You will record the angles and suddenly you will see the jump and you will detect it. And when you detect it, you go back to your transient flow velocity. And you can do this systematically. It's completely programmed onto the wind tunnel system. You can repeat it for 200 runs, fully automated on the wind tunnel. And you can also do it in both directions by having the transient flow velocity on the other branch. You can either start like here at 25 degrees, or you can start at 65 or anywhere else. The problem is if you stay around here, you don't know if you're going to cycle on one way or the other. So you have to be careful about that when you choose a transient velocity inside the hysteretic cycle. So first, since we are looking at it not as a fluid dynamic system, we're going to look at it as a generical system. So the first thing to do is look at the time distribution. So we're going to look at this kind of time tau and look at its distribution. If we place ourselves around here, for instance, we will record all the events we have and look at the probability distribution. So the survival distribution looks like this. So it's an exponential distribution from which we can extract a characteristic time tau c. And so we're happy we have exponential distribution. So all our events are independent. So that means that we don't have any experimental bias from the system. We expected exponential distribution, and we have that. And if we now look at further other points in the cycle, we get this distribution of times, and we get characteristic times that goes from about 1 second to 100 seconds with events more than an hour, that last more than an hour. And so we see that the closest we are, the smallest the characteristic time. If we now take the reverse transition, we also get the same kind of distribution. So it seems that we can have times on both directions that goes from a few seconds to 100 seconds. But there's one thing that I haven't said, is that we have to be careful of one thing. The experimental control parameter is the flow velocity. fixed by the rotation of the motor. The true physical control parameter is the aerodynamical torque, which is proportional to rho u squared. And the problem is rho, by using the perfect gas law, is proportional to P atm over T. And the problem is when we are in Lyon, we have heat waves and we have huge storms in summer. So we have to be careful of these two things. In particular, instead of looking at the test velocity we input, then we will look at the sine theta we record, because this one is going to be the true equivalent of the aerodynamical torque thanks to our fundamental equation. So what are the implications of this onto our data? So instead of looking at the slice that we had before at constant u velocity and we get this probability, we look at this kind of system where we have the sine theta here. So the theta I is the initial angle over the time tau, which we record, and tau is tau. And if we have something that was quite cool, where there were no storms, there were no change in temperature over the data, we get something that's great. Because for one flow velocity, we get only one sign on average. And the problem is, if we put all the data together, you see that it's no longer any lines. In particular, while doing the downward motion, we see that it's more like curves of data and absolutely not straight lines like we can see here. And it's equivalent to looking by slice. If we now reslice it, we get the same exponential distribution, and we can get the mean value. The characteristic time is the mean value thanks to the properties of the exponential distribution. And so we get to see by looking at the 2D probability, we can still recover the characteristic time. And this characteristic time can be fitted by a double exponential. In particular, we need another fundamental time, which we will call tau 0, which is different for both sides. And it's about 0.10 seconds for the upward transition, drag toward lift, and the downward transition is about 0.11 seconds, so lift toward drag. And in particular, we can look that it's truly a double exponential when we take the double logarithm of the ratio between the two times, and we get these beautiful lines. And it's not only reserved to astrophysicians to get some double exponential, we also get that here. And in particular, this kind of behavior exists in a completely different phenomenon. So we have them on our pendulum, and it's especially true in the transition to turbulence. So I will do a bit of introduction to the transition to turbulence, only to introduce what I'm going to take from it onto my pendulum. So as you may all know, when we have a pipe flow and we increase the flow rate, the flow speed, we get from a laminar flow to a turbulent flow while going through an intermittent regime where we have puffs of turbulence that exist and then disappear or double or anything. So these were first done in 1981 by Reynolds, and then recently in the early 21st century, we got some new experiments and some new modelization simulation to get more data on what's going on. In particular, what we know is that these puffs have a particular life. And this is what is going to present this kind of double exponential. In particular, if we have here a puff, so it's in color here, at some point it may just disappear. But it can disappear at almost any time, or it can never disappear. And we can record the survival distribution for these puffs. And by changing the Reynolds number, we can get various characteristic time for this disappearance. And so we can get this kind of dependence of the of this characteristic time as a function of the Reynolds number, and you see it's a double exponential. You can also look at whether the path suddenly splits into two parts, and so this is going to be the second part of the graph, which we won't comment too much today. So what has been observed in the transition to turbulence is that we have this observation of having exponential distribution at fixed Reynolds number with a characteristic time tau, and then we get a super-exponential of this characteristic time as a function of the Reynolds number. In 2010, a phenomenology was proposed by Goldenfeld and collaborators that the turbulent path decays when its kinetic energy is not high enough to sustain turbulence. In particular, during a time tau zero, which we call tau zero of turbulence, which is the correlation time of the turbulent path. And so we're going to extract a threshold below which this kinetic energy has to be below for this given time tau in order for the path to decay. And by having Gumbel distribution of this probability of the maxima, then we get that the characteristic time is a double exponential of the Reynolds number. Not really on the Reynolds number first, it's on the threshold. But if the threshold is depending linearly of the Reynolds number, then we get the double exponential. And they observe that they can do more or less coherently this kind of explanation to get the double exponential, which fits kind of quite well if we look just at the data right over there. And so what we have for us is like, oh, we have this kind of thing for the decay of turbulence, so why can't we do the same for our transition in the pendulum? Because we also seem to have the super exponential. And so we propose the following phenomenology. Our lift state is no longer sustained if the fluctuation of torque, so we are not talking about kinetic energy anymore, we're talking about torques, because for us, the thing that is keeping us on one state is not energy, it's torque. And so we're looking at this distribution, and we're looking at whether that's not strong enough upward. Like if we don't have any fluctuation pulling us, then we will go back to our drag state. And this during the time tau zero, which is going to be the same tau zero as before, the 0.10 seconds. I will explain later which tau zero it is. And so the question is, do we have Gumbel distribution so that we can do exactly the same phenomenology? Because if we have Gumbel distribution, then maybe the threshold is going to be linear on the sine of theta. So maybe we're going to have our double exponential, but just by following the same phenomenology. So before going like this, we have to know what are the probability distribution of the max of delta gamma. So we remove everything we know from gamma error, so the aerodynamic torque. We just say, okay, it's we reverse our equilibrium equation, dynamical equation, and we transform theta and theta dot dot into the aerodynamical torque. And so we get from this kind of signal to this one. And for those who may wonder, these peaks do have a signification. It's not pure noise due to the double scaling, the double derivation. And we will then remove the mean value and just look at the fluctuations. And then we will take sections of size tau zero and record the maximum. And we will get the delta gamma max and look for multiple windows of tau zero. We will get all this kind of maximum fluctuations, and we will look at its probability distribution. If this is going to be our max of delta gamma over tau zero. And if we look at its distribution, we get a Gumbel distribution. For those who are not familiar with the Gumbel distribution, you see it's utterly asymmetric. And another particularity is that the mean value is not the mode. We have the mode is below the mean value, And we can look at two different domains. One is the extreme events domain, for which the probability of an event of extreme intensity is higher than Gaussian. It's almost exponential. While we have on the other side what we call the rare events, for which the probability is below Gaussian. And even though we are close to the mean value and close to the mode, we have a really low probability of occurring. So that's why we call them rare instead of extreme. So how are we going to go from delta gamma to the threshold, delta gamma C? So we're going to look at our Gumbel distribution, and in particular, the cumulative distribution function. This is where the double exponential appears. In particular, it's a function of the mode here and of the standard deviation multiplied by a factor, which is not relevant at all. And the phenomenology proposed by LMFL says that this probability is equal to the time tau 0 over the time, the characteristics time tau c. And so for us, we're going to rewrite everything like this. And what we know is all these green variables. We know tau c from our beautiful eagle wings, as we call them. And we know tau 0 because we haven't fitted them, in fact. We know them from just what I'm going to explain later. And we know sine theta, of course. And we can get mu and beta from this PDF. So purely dynamical. We have no, here we don't suppose anything, we just use the signal and get this data. And so we can rewrite it like this and get the delta gamma C over beta. And what we have here is that it's linear on sine theta. So we have our double exponential right here. And in particular, the two curves here are exactly the same slope as here. So this one was completely, we never looked into the dynamics for fitting these curves. So we're quite close to what we wanted. We have a threshold that is linear in the sine theta, and the double exponential seems to fit well. And a particularity that is to notice is that if the characteristic time is more than 3 times to 0, so about 0.3 seconds, which for us is always the case, then the threshold here is always below the mode. So if we look back onto the Gayout distribution, then we're on this part of the system. It's rare events that's triggering our system, and not extreme events. So the take-home message here is that it's not strong exiting fluctuations that make some transit, but however the lack of returning fluctuation. It's not because we kicked towards downwards that we're going downwards. It's just that we're no longer restrained to be up. And so you can find the details in this paper. So now that I've talked about tau 0 that much, in fact, tau 0 is something we found in the spectrum of the system. We looked at our dynamics of theta and looked at the spectrum and have this beautiful peak here, which is going to be 1 over tau 0. And so first, it's not the pendulum frequency. Our pendulum has a frequency of about 1 Hertz, and here it's about 10 Hertz. And so it's probably a flow-induced frequency. That's the other thing that is going to produce us a frequency. And in particular, we think of vortex shedding. And in particular, if we use the standard dimensionalization, we get a Strouhal number of 0.07, which in the literature of disk aerodynamics corresponds to what they call a transverse Strouhal. So the question is, what is a transverse Strouhal? First, what is a Strouhal, in fact? So if we look at the weight behind the cylinder here or sweep here, we can see this vortex shedding vortex, contra-rotating vortex shedding at a periodic frequency, FBS, and we can then define the screw-hole number by multiplying it, and then we get for a cylinder a screw-hole number of 0.20. For this, then, for a 50 degree, we get 0.27. So you're like, oh, it's really far from 0.07, right? But in fact, the problem is our system here, we only look at one plane. Our disk is 3D. In particular, when we place it close, normal to the system, we get this kind of hairpin vortex. If we further increase the angle close to 30 degrees, we still have a bit of hairpin vortex. Then we get more puffs, which still are, so it's a different way of looking at it. So it might not be obvious that it's also a bit of hairpin-like structure, more annular at the end. And then when we further increase to here 60 degrees, we get something that looks really close to an airplane, in fact, with two contra-rotating vortex, really stable for a long time. In particular, so we can look at below stall, in fact, we have this ring and hairpin vortex, and above we have these two vortex waves. And in fact, the problem of these hairpin vortices is that they induce another frequency, which is called the transverse screw-hole, and it's about 0.07. So in order to further look into it, the problem was that all these data were produced for Reynolds number close to hundreds. We are at Reynolds number close to 1,000 to 10,000. So we're not sure that all the simulation and water experiment are relevant to our case. So during my thesis, we did a bit of static visualization of our wake. And so we did particle image velocimetry. So naturally, we have a high-speed camera. We've got a smoke machine, laser, so two small laser of 5 watts power. And we get a visualization region of about 15 by 15. So I said before we were looking at disk of 4 centimeter. For this, we're looking at disk of 6 centimeter diameter. So in order to have a better view on the structure and get a better resolution. And we're placing ourselves at about 10 centimeters from the edge of the disk. So I don't think I really need to enter the details of PIV here. I think everybody is more or less familiar with it. So I skip this. So we are then extracting the flow the vorticity from the flow field, and we can detect the edge. So we're not using the Q criterion. We're just using a criterion on the envelope. Like we take the ISO surface at the maximum vorticity over square root of 2 for convenience. And then we get the radius and the distance and everything. But today I will only focus on the ISO surface. In particular, look at how it depends on the angle. So we're looking here at spatiotemporal evolution. So the vertical axis is time, and horizontal axis is the horizontal transverse to the flow. And we see an evolution with the angle. From left to right, we go from the vertical to the horizontal. So first, we see that between 0 and 20 degrees, we don't see any really coherent structure. In particular, what we know from the literature is that it's mostly ring vortex or hairpin vortex. And the problem with this is that the main vorticity is inside the visualization plane. So when we compute our vorticity, it's not relevant. When we go for 35 to 50 degrees, we start seeing this kind of pulse of vorticity, which seem almost at constant frequency. So we're happy because it seems like a straw hole. And we get this hairpin vortex-like structure with an angle-dependent frequency. And this is coherent with what was looked at in simulation for about Reynolds 100. Then from 50 to 80 degrees, we get something almost straight and almost in particular at 60 and 70, we even see that it's no longer collapses. We only have constant vorticity, really stable, and it's really close to what we have behind an airplane. And when we are above between 80 and 90 degrees, we see that there is some noise occurring. So we're not really happy because we have noise from the support. But the positive part is that we don't see it for our relevant angle region, which is between 40 and 60. So we do have it, so we can't really explore the dynamics of the system above 80 degrees. But at the same time, what interests us is in between 40 and 60. So we're going to be completely free from all the support noise. So if we look back at our bistability range, then we can see that below 50 degrees, so on the drag-dominated regime, we have something that's more of a ring and hairpin vortex, so something really 3D, while when we are above it, we've got something close to an airplane with two contrarrotating vortex. And so we're going to bring everything together and look at the wake during a transition. So we're going to sync the PIV measurements with a transition. So if we have this kind of signal, then we input a detection instruction. So if the pendulum crosses this line, then we will send a signal to the camera to trigger it. We will then place the pre-trig and post-trig in order for the camera acquisition to lie around the transition, in order to be sure that we have a bit before the transition to see precursory events, and a bit below if we see some change before the after the transition. And so we can look at the wake change during the transition, but first before and after. Is there any change? So to see it, we are looking at the standard deviation over this period of half a second, and we look at its map of the standard deviation. So there is a mean flow field, but it's not really changing at all, so we weren't so much looking into it. And in particular, here we have these two lobes here of intense fluctuation, about 1 meter per second fluctuation, and this is the horizontal velocity, and this is the vertical, and here we have something of a horseshoe shape with a strong, really strong fluctuation here, above 1 meter per second. And so this is for the drag state, and for the lift state here, we've got about the same region, but placed differently, despite the fact that it's only 6 degrees difference. So the projection of 6 degrees is really low, but we see that the horseshoe jumped a lot and reduced a lot as well. And the fluctuation is really low. So the color scale is the same, but here we only attain about 0.7 meter per second. And in particular here, it was almost a heart shape for the drag state, but here we only have really two small fluctuation zones. And so we observe a change, but what can we understand from the change? Can we get insights on the changing itself? In particular, there is two zones that we are going to be more to get more insight of. Is first this region of intense fluctuation in both directions. So in particular, we think that it's due to the longitudinal vorticity, so the one which is orthogonal to the plane, which we can compute, and it's probably this fluctuation goes from due to the oscillation of the vortex center. When the vortex center varies in place, and when its intensity varies, then we get huge fluctuation of flow velocity. So this might be the region where it happens. On the contrary, this position, which only occurs on the vertical direction, then it might be due to transverse vorticity parallel to the visualization plane. In particular, it might be the signature of the trailing edge vortex. This is where we expect it, and we have strong fluctuation. When a trailing edge vortex comes in, like if I have my vortex like this, then it goes like this and like this. Then when it crosses first, we get upward flow velocity, then nothing, then downward flow velocity. So we're gonna see some huge standard deviation in this part whenever a trailing edge vortex crosses. In particular, we can look at spatiotemporal in this region. So we take this line of flow velocity, we place it like this, and we look in color at the vertical flow velocity. Above is the vertical velocity for on the line which corresponds to the intensity on the upward position, and below is the one from the downward position. As you see here, we've got a band of lines. Positive, negative, positive, negative. Not really. We have a mean value because of the downward of the vortex, but overall, whenever there is a couple dark and light band, it's a vortex shed. It's a trailing edge vortex that's crossing our plane. And so we can see that up to a certain point here, then we get really intense vortex shedding on our bottom line and very few on the upper line. When suddenly on the upper line, we get some vortex shedding occurring. So we detect, we seem to detect the displacement of the leading edge vortex, of the trailing edge vortex. In particular, what we need to be careful of is that the synchronicity is made between is made through the trigger of the camera. So whenever we have something that's happening at the pendulum, then it's after what's happened on the flow which we record, because we are further downstream. So the synchronous events are the red vortex and the red oscillation, but the oscillation produced by the red oscillation is the green vortex, which we will record way later. And so this displacement seems to be at the same time of the start of the fluctuation. So the displacement occurred before the bistability, before the transition. So for now, we have observed a restructuration of the wake before the transition due to the synchronicity. It seems to be a displacement of the trailing edge vortex. And so we think that the flow trigger transition is the change in the wake structure. However, we need to verify that it's rare event. It's not something that happens regularly. And in particular, if we stay close before transition, do we see this kind of event of restructuration? For instance, here we see something that seems to go downwards. So maybe here there might be something else happening while the transition is not completed. And we also see, in fact, a bit of change around the fluctuation of the oscillation of the oscillation of the vortex center here, which is really intense before the transition, and then around the transition lowers a lot. So we think that it's a global restructuration, but we still need to further investigate it. It was at the very end of my PhD that we managed to get this kind of data, so the treatment is still underway. And so I will now go beyond the disk pendulum. So everything here was made with a disk pendulum, but we can do many other things. In particular, we can change the aspect ratio. So here you have the 8 different aspect ratio we tested. This kind of strange aspect ratio comes from the fact that 4 to 15 is the aspect ratio of a tail feather of a pigeon. And then it was to optimize the number of plates with the small plate we had of the constant thickness. And we used Eiffel data, which looked at the aerodynamic normal coefficient with respect to the aspect ratio and with respect to the angle over the whole 90 degree, which is really rare at that point. And we see that here we get this trend behavior for which around 1 we've got a huge stall, and we recover it here at 4/7, we have this huge stall, and we can then, we have a quantitative agreement, a qualitative agreement, but not quantitative for now. But we weren't exactly in the same configuration as I thought. We got this by inverting our equation using just the pendulum. So instead of having a force sensor, which might be a piezoelectric sensor, which might drift over time, we had just had our pendulum, and we record this angle. So there might be some fluctuation due to this approximation of the flow velocity at the point of the pendulum and everything. But we recover this strange behavior of first something that seems quite smooth, then something that peaks for around 1, and that gets smooth again. And we can then compute the stall angle, which we can define as a stall angle, as the last at the maximum of curvature of the aerodynamic coefficient, and look at its evolution with angle. I haven't presented it here, but it's in my PhD. And we can also play with porosity. And for this, we used a fly swatter. So this is the fly swatter we used. We just bought it for €2 on Amazon, and then put it in our wind tunnel, and then taped it. We taped it with many kind of different configuration. I think about 16 to 18 different configuration. And we get, for these 4 configuration, we get a bistability. We get this stall that appears, and then if we tape it just differently, but we can still tape the same number of holes, then for all these configurations, we have no bistability. And what the common point between all these configurations that have no bistability, then a part of the leading edge is not taped, while on the upper part, the whole leading edge is taped. So we conjectured that the interaction between the leading edge vortex and the 2 trailing vortex was fundamental. If even just the edge were not taped, so the trailing vortex cannot form, then we get no bistability. When we then tape the edge, the bistability arises. Apart from this, we also used our pendulum as a weathercock. We would remove the weight of the equation because we thought, oh, maybe we can reconstruct the aerodynamical torque just by having the pendulum go from 90 to 0 degree, because its equilibrium position is at the horizontal. The problem was the quasi-steady approach, despite everything being at low speed and everything, was not sufficient. So we proposed 2 models in order to reconstruct it. And we have a paper currently under review about this. One is inspired by the vortex-induced vibration, and the other from more empirical, using dynamical reconstruction of the aerodynamic coefficient. And also, our system is much richer than what I proposed before, what I exposed today. So first, we can have the transition in both directions for constant flow velocity. In our previous pendulum, we couldn't, especially the intersection point of the for one of the 2 exponential was at about 10.14 seconds. So we need to wait on average a universe time for it to transit in both directions. So this is definitely not something we're going to see in the experiment. While when we change slightly the equilibrium of the pendulum, we can get transition in both directions. We can also visit the unstable position, either during a transition, so we just hop around the equilibrium position and measure its time, and we can see it on the phase diagram. So we can, and we also have overshoots. These overshoots, however, only occurred when we had a potentiometer, so we suspect them to be linked with damping mostly. Because whenever we had the encoder, the frictionless encoder, it would disappear inside the whole fluctuation of the system. And we can get excursion. And so excursion here, we get this, what I would call incursion inside the historical cycle, Well, suddenly the pendulum goes way behind inside the system, but comes back. And every time it does this, we get a signature on the torque fluctuation. And these are the peaks we saw before. So, for instance, here we have a series of two excursions of 4 degrees, so a huge excursion. And then every time we get this V-shape system. And when we have something like this with a huge amount and then a slow descent, we have an M shape on the torque. And we can see this anytime. And so what we want to do with this excursion is get more statistics. Because if we get more statistics, then maybe we can do the same as our transition and get a model for it. Also, there is much more PIV measurements to do by looking at the dynamical PIV. For instance, I suggested before that we don't know if our restructuration is common or rare or anything or extreme. So we need to look into it. And we thought also of proper orthogonal decomposition to extract the noise from the vorticity and everything. And also what I started during my master's thesis but couldn't follow in my PhD was the influence of turbulence. We can get this kind of diagram for which we can define the hysteretic zone, the lift dominance, drag dominance, and bistability disappearing completely above the critical turbulence rate. And lately, there is many other things to do by control and coupling. If we put 2 pendulums with a certain angle, one can be in the drag state, while the other is the lift state. And so maybe there might be more than 2 by stability. So we can maybe get something that has multiple 3 to 4 by 4 equilibrium position by embedding different pendulum like this, either with a straight rod or with a torsion spring. So there's an infinite number of things to do. And lastly, if I have enough time, I don't know if Francesco, I still have time.
Yeah, if you want to take 5 more minutes, that's okay, and then we can start with questions.
Okay. Yeah. So during my PhD, as you introduced, I developed a project on butterfly flight, and so I will just introduce it briefly. So for those who don't know, when butterflies fly, they have this production of vortices, like first a vortex ring that spins in one direction, and then when they flap back, when they upstroke, they have the contra-rotating vortex that occurs. So it reminds a lot of our pendulum. So maybe there's something to do together. And in particular, when in natural flapping condition, we have this 3-way coupling between flapping wings, flapping patterns, the vortex they produce, and the lift production. So in order to dissect this 3-way coupling, the conventional approach is to play on the flapping motion. We get a robot who flaps a given way, then we put some PIV measurements to record the vortex, then we put some sensors to get the lift and everything. But our innovative approach is to play with lift. So we're going to put our butterfly in different condition where it needs to produce different lift and use its natural intelligence in order to get the flapping pattern it creates by adaptation. In particular, so this is Project Phoebus, so flight observation of butterflies under space-like gravity. And we take this beautiful butterfly, well, not this one, but another one. And we know that on Earth, its flapping patterns look like this. And in particular, because evolution has made its way, then it produces by these vortices lift and thrust at the same time. And on average, lift, balance, weight. And so the displacement is horizontal. If we now place the same butterflies in different gravity, so in microgravity, on hypergravity on a rotating table, then if it flaps the same, it will also produce the 2 exact same forces. But now it's no longer compensates the weight. It's going to have a vertical bias on its trajectory, either upwards in microgravity or downwards in hypergravity. So we started doing tests if it's work, yeah, in hypergravity. So we place this kind. No, sorry, I'm spoiling. Yeah. So we place. Oh, a bit low. Yeah, we place our experimental setup onto a rotating table, and we spin them at 25 meters per second. So this is slowed down, and we manage to get some flight of the butterfly. And we're currently analyzing the data, but what I can tell you is that this butterfly on Earth flaps at 14 hertz per second. When here, it flaps at 15 hertz per second. It increases flapping frequency. We don't know much about this butterfly in particular because we still haven't looked too much into the data, just extract the flapping frequency, which was really easy to do. We still need to look at the kinematics because his wings just seem to take not so much amplitude. But we started doing some flight reconstruction on this butterfly, so Greta Otto, which is our kind of favorite butterflies because it's almost completely transparent, which is kind of beautiful for butterflies to be transparent. And we managed to reconstruct its trajectory, and we started doing some numerical simulation to get the helicity and the force production. So for now, we only have this on Earth in 1G at the control experiment, but we're going to input the data for the flight kinematics we recorded at higher gravity level. So I will conclude on this, and maybe in a few years you'll get to see more of this with the whole results about this campaign. So I thank you for your attention, and I'll take any questions.
So thank you, Ariane, for the very interesting presentation. So I think we can start with questions. So is there any question in the seminar room? In the meantime, I will check the discussion. If someone has questions, invite in the discussion. So please go ahead if you have any question inside from the participants inside the seminar room.
You relate to the flow around the disk.
Yeah.
I didn't say much about the flow on the disk.
Yeah.
Which may be separated or not, or may have a separation bubble or not. The separation bubble may oscillate or not.
Yeah.
And actually, this would surely also be related to what happens around.
Yeah. We haven't looked into it because it would require a much more complicated setup in order to have the 3D composition of the wave. Especially here, we focused on the transverse vortices because we kind of expected it to be in that direction that something was happening. But the fact that at the end we get some displacement of the trailing edge vortex seems that maybe, in fact, what they call the transverse throw hole, which isn't really understood yet for the disk, as there is so few studies about it, might be in fact the pulsation of the leading edge vortex that might in fact cause the trailing edge vortex to move around here because of the pressure varying on top. And then also then it might make the two trailing edge vortex interact with each other closer due to the size varying of the leading edge vortex. But
it's natural to expect, I mean, if the flow is attached, we have more lift and drag. If it is detached, we have more drag and lift. It's very natural. And then, of course, according to whether you have a separation bubble which oscillated or not, you can again naturally see the oscillations.
Yeah.
So it's a more natural, at least full mechanical way to look at it, perhaps.
Yeah.
And clearly, of course, when you have one or the other, you'll have around it, you know, the shedding will be different.
Yeah, we wanted to do some surface measurements by having some gray and oil on top of it, but we didn't have time to implement it because of all the setup it requires. And we think that the problem is the change in angle is really slight, and so we're not sure that if the recirculation bubble is attached and then detached, then it would occur about 1 degree. So it's more like the 3D structures that change overall, and there might never be any reattachment because of the 3D structure. And maybe even before, like at the very start of the bistability, for instance here, it might already be detached, and we wouldn't know because the two trailing edge vortex are so strong that they manage to keep everything stable. While when they arrive here, then they get destabilized and then suddenly collapse and drop. That's what we think, more or less, but we're not sure. We really need some more insight about the visualization of that part.
So let's see if there is someone from the audience, from the virtual audience, who would like to ask a question. Just feel free to unmute your mic and ask your question, or you can write in the chat. I can report the question. And I don't see anyone for the moment, so I do have a question myself. You kind of draw kind of a comparison between transitional regimes in turbulent pipe flow, in transitional pipe flows, and your system, where basically you recall somehow also the modeling approach of Berkeley for explaining transition and including intermittency in the mathematical model. And if, as far as I remember, he was actually doing that by including kind of a double hump potential, kind of a cubic potential, fourth order potential, in which you have like two humps, and so you get it's three different equilibria. And this seems to be somehow your case, but so the question is also, do you observe any sort of intermittency? And if you do, how do you link it to his model? Because to get the intermittency, he needed like a transport term, which I'm not sure if you can really link it to the memory term of your flow somehow.
I wouldn't know about the intermittency. Possibly when we have the systems that transit in both directions, we might see something close to it. But here, when we for this part, we were really separated. We had one transition in one direction, and the other completely different. And regarding the fourth order potential, in fact, it's hidden here in the fact that the threshold is linear in the Reynolds number.
Yeah.
And for us, in fact, we completely removed everything about it and just computed the threshold through our experimental data. And maybe we might be able, what I didn't comment before is when we first did the first exponential fit here, we had sine theta 0 and eta, which were data from the fits we can't get back from the second double exponential fit. But what we suspect is that maybe sine theta 0 plays the role of the last point on the bistable regime we can extract, in fact. Here it's the one for which tau equal tau 0 times E directly. And after that, we never can see anything about any transition. It's no longer defined. And eta might be linked to the potential shape, in fact. What we suspect is that it might be related either to the curvature of the potential or maybe the third order of the potential because it seemed to be somehow connected to the curvature of the normal coefficient. But we need to further look at different shape and different conditions in order to be sure what sine theta 0 and eta are. But this might be the link with the fourth order potential, I think.
Okay. But as far as I as I understand, you correct me if I'm wrong. As far as I understand, basically what you the main difference between the dynamics of your system and the dynamics of the simplified dynamics of Berkeley systems in phase space is basically your system has a really sharp somehow hysteresis loop that kinds of end up in a potentially in a limit cycle, whereas in his case it's kind of a chaotic loop.
Probably, yes.
Okay. So that would make a qualitative difference between not observing and observing the intermittency, basically. Okay. Okay, so thank you. And let's see if there is someone else who would like to ask a question. Is there someone in the room? I don't see it very well. Is there someone in the room who would like to ask a question? This doesn't seem to be the case. So let's see. I don't see any question in the discussion. Let's see if there is someone else who would like to ask a question from the virtual audience. So just feel free to unmute your mic and ask a question if you want. Okay, I may have a last question and then sorry, that it's a very interesting problem though. And so you talked about control when you considered at the very end, like some of the perspective of your study, like when you include two penduli and do you have something in mind, or it's really like because a system with two penduli is kind of quite difficult to handle. I mean, the phase space becomes enormous, and I mean, and probably very difficult to characterize. So, do you have something in mind, or just
at some point, we couldn't really go far in our collaboration, but we discussed with Mohammed Farazmand in North Carolina, I think, who wanted to propose us with control, but mathematical point of view, with kind of a spring attached to the system to do some control and try to induce the bifurcation by adding some new terms and try to dampen this bistability. But maybe what we want to look into with the two pendulum is that if we fix them with a constant angle in between, then we only have one pendulum with complex geometry. So the equation of the movement is much easier, but at the same time there might be coupling between the aerodynamics on the two different systems and also in between. They might interact with each other. So for instance, if one has two straight vortex while the other has a vortex ring, then maybe the vortex ring can perturbate the other, so it might go downwards, and we might either couple them or just have them completely separate and only aerodynamically coupled. And so really, it's something, for now, we don't really have any thorough idea of what we want to do with the control, but there might be also by changing the rugosity of the system, if we can dampen the stall while not inducing the decrease in the lift production or anything like this might be of interest.
Okay. Very interesting. So thank you very much for the presentation. So I also invite the audience to thank you once again. It was very, very interesting. Thanks for presenting. Okay, so I think we can close the webinar now, and thanks again for having accepted the invitation, and have a good evening. Bye everyone.
Bye-bye. Bye-bye.